Okay, just a second. Share screen. Okay, do you see now?
Yes.
Okay, perfect. All right. This is the first thing that I'm showing you. I did not show anything before that. So that shows, as I said, the Canvas gives me an opportunity to see how much time somebody spends interacting with us, with Canvas. Not just turn it on and stay idle. All right. It does not measure. It's like, this is not what it does. There's an algorithm that gives you that interaction. And then you see here 4 different students. Of course, there is no, I removed names and everything. I put also, I changed the scale. So they measure, this is from 0 to 100, whatever. I don't know what that even means, but it just shows the trend. And then this is from 0 to 60. So you see, like the less time, the more time you spend. This is a top student in the class. 95%. Even at the time, obviously the individual had power here. This is the week when the power fell, and then was able to interact with the software, and obviously to spend time doing things on Canvas. The second is 85%, and then as you go down, you see the correlation between how much time you spend with the material and how well you do. So practically is exactly what I told you. In this class, you're always you're all very smart. And the only thing that makes a difference, the only one thing that makes a difference in this class is how much time you spend. So that is one thing that I wanted you to see in practice. So when I'm telling you that, it's not just I'm gonna make you study hard, it's because this is what experience has shown. Now, here I want you to tell me, there are 2 cases, A and B. One of these cases, it was a student who has performed 92% in the whole class. The other case, and I have also changed, so you have, this is from 0 to 60 in the lower case. This is from 0 to 100 in the uppercase. Which of these 2 students has observed it, however, which has performed 92%, which has performed 85%. So can I hear some suggestions?
A is 92%.
A is 92%. Okay. Anybody else? I'm not going to tell you yet, so I'm not showing any response to reveal. So
Did you
anybody
say
else?
B is from 0 to 60?
Yeah.
I think 92% is B.
Yes.
Rip.
90. What is the difference between the two?
It's like more consistent, even though it's a little bit less than A. It's more
Yes.
it seems like it's more consistent and
Yes. You remember what I told you in this class? If you spend less time, but throughout, less time. So in fact, the interesting thing is that both A and B, I selected them. So more or less, the total time is about the same. But one student has spread the total interaction time, whatever that means, over the whole time. The other student does it only at times. All right, there is no consistency through. The other student, even a little bit of time, look at the time when the other student had 0 interaction. Look how small the interaction the B student had with the material. Even small interactions with the material will help you learn better. So if you stay away from something for quite some time and then you spend an enormous amount of time to learn it, it's not going to help you. It's better to put aside a little bit of time every day. You're going to perform. The difference between 92% and 85% in the class is huge, as you know. And that is because the second person, and look, it's out of 60, the person did not put, the other person was killing himself or herself. I don't even remember who these individuals are. the person A was spending an enormous amount of time at specific times. Person B spent less time, but throughout, less time every time, but it was throughout. And then you can see the difference. So I'm just telling you, and believe me, don't let go for so long. Then you have then to relearn it again. It's a waste of your time. I don't know how else to tell you. It is a waste of your time to let go for too long, for days before you come back to look at the material. And then you're not going to even perform well after you have wasted all of your time. So that's what I'm going to tell you. That's the only thing that I have. And I want to see if you have any questions about anything, and more specifically about your homework or about your whatever comments you want to give me. I have another few minutes and then we'll start the lecture.
Professor,
Yes.
did you say the grades were posted for the midterm exam or just the solutions?
Did I not post the grades? Let me see.
I can't seem to find mine.
You know
I
why?
have my grade.
Oh, you have your grade?
I have mine
Yes,
as well.
Professor.
Okay. Well, I thought I made the grades available. Who does not? Could you tell me your name? Who does not have your grade?
It's me. Last name's Rustenbeck.
Okay. I'll make a note and then I will check it out. All right. Just
Okay,
in
thank
case. You never know what happens with the software. Just in case, Rustenberg. Okay. I will check it and will email you.
Okay, thank you.
You're welcome. All right. Any other comments, questions?
I have one question about the algorithm with Canvas, in which it can see like how much time you've been
Yes.
working on Canvas. So I have the online like textbook, and I like to like do some problems from there and like go through that. Can it check and see if I've opened like the online textbook, or like check and see if I've like spent time working problems through there, or does it only, or can it only see like?
It is only on Canvas, whatever, whenever you have to get on Canvas for the algorithm to work. I have many textbooks myself, which are online, and I don't go to them through Canvas, obviously. I'm going there individually. This Canvas logarithm, I have to tell you, algorithm, I don't know very much about it. I don't know how they measure. I don't know even whether it is, how meaningful it is. So that's why I don't know what this 100 means, and it's not important. But they do record in some ways effort versus time. And how do they do that? You can argue about it, but yes, whatever you do outside of Canvas is not gonna show it. The only reason I'm showing that is because we have a lot of material on Canvas, all of it. Whatever we have for class, you have to find it through Canvas. I don't send material via email and everything. And so it is the only, I have to tell you, it is the only indication that I have. So take that into consideration. If people spend a lot of time outside of Canvas, obviously it's not going to be reflected. The only thing that I did, and that's why, I don't use that for any other reason but to make correlations, to tell you the truth. It's only good for correlations, nothing else. And correlations, always considering that there are so many other parameters that are not counting here to the whatever you see. But I also have to say the correlations of time on eCampus versus performance and this one, yes, they are good correlations. They are meaningful. That's what I'm saying. Let me put it this way. Any other comments or questions? Do you have any questions about your homework? This homework is going to be important. The 80 points that I will give you, it's bonus. So it's not going to count towards the total because I put 0 when I created the assignment, I put a 0. So it's going to add a 0 to your number on Canvas to your total. And the reason I did that is so I can use it as a bonus. Because if I did not put 0 there, when it says how many points you're going to give, I will give you up to 80, but it's not going to count towards the total of your grade on Canvas, which for me is useful to have, because I don't want to add all of the numbers myself. You know, otherwise I will have to subtract numbers before I get, and that becomes a mess for a class of this size. Any other comments? Yes.
I was gonna say, so just to make sure I'm understanding them. So us turning in this homework, which is the test corrections, basically. I believe at one point, I believe it was we got like half the points, but are you saying now, to my understanding, that you get 80 bonus points for turning it in? Or
80 bonus points.
up to 80, or
Which
just-
means you're gonna, when I looked finally for a final count of the points, I will look at the count that I get from Canvas. That's gonna be, and then I will import from Top Hat every time, all right? So those will be incorporated. Everything, therefore, all of your activities at the end, it will be incorporated. Then I will look at this, and then on the basis of those totals that I get from Canvas, I will create the grade scale. What point A's, B's, and so forth. Then I will add to each one of you all of the bonus points. And then I will see where you move on that scale. I'm not going to change the scale, obviously. If there are, usually the top A+ students, something go above it, which is fine, they keep their grade. But then other students will move higher if they get bonus points. So you may be able to change your grade like this from your bonus points. Did you understand what I said? It's a little complex, but that's how I'm doing the grading.
Okay. Okay.
All right. And this is in addition to other bonus you're going to get. As we go through the last 3 weeks of the class, I will also update the other bonus points so you can see them. And I will create a separate column within Canvas to see your bonus points. The total bonus points for each one of you, so you can see them. Okay.
I've got one more question.
Of course.
Based off of like the exam scores, like what would be considered, like what range would be considered a pretty good grade for the exam? Or it shows that we've been well
Usually
prepared.
above 90% is a very good grade for A.
Okay.
And I think it's consistent. It's not out of a range. I also try to stay close to what is considered to be the traditional grading scheme. So that's what I would say. If you are below 90 with your bonus points, you can go above that. That will give you a different grade. Now I'm suspecting because I need to see at the end, all right? But 90% is a very, you know what you're gonna get, that you're gonna get a good an A in the class. You may go below 90, depends, all right, obviously, but the 90 is for sure. Did this ask your question? Did this answer your question?
Yes, I was just wondering because I know that like I know in total in the entire class, an A is a little bit different than the traditional like 90 points is an A type of thing. So that's why I was just wondering.
Yeah, well, it depends so much, all right? It's very hard to say because it also what I said I do. I always look at the maximum. I don't get the percentages out of the hypothetical maximum. I consider as 100% the maximum that a student did in class. That's my 100%. And then I go from there. So if, for example, in the class, the maximum number was 95 or 92, let's say, which was not in this case. But if the maximum number is 92, of course, it's not going to be from 92 to 90. It's going to be an A. It's going to be lower than that. See what I'm saying?
Yes.
Yeah, okay. All right. It's a little complex, but I think it's more meaningful this way. that I do it. I have tried different things over my career, but I think I feel more comfortable with this one. And then obviously, we're going to talk a little more about this as well in the last 2 weeks, definitely, of the semester. But I will give you, I'll try to give you, I have graded, obviously, I need to add the grades for the team homework. But the team homework, I have to tell you, 90% of the class has done very well in the team homework. And the reason for that is, first of all, it gives you good points, but also you have an opportunity to work with your colleagues, and then we are going to have team homework from now on until the class, so that just you get a little more opportunity to collaborate. Okay, let me then start. I will stop sharing here, and then I will start sharing on the other one to continue with our, 1 second, with our continuation. We will finish this week. We have two lectures because Friday is off again. So we will finish inductances, and then, so we are going to start talking about transmission lines, but we will only try to introduce them, and then start 11th, 12th, and 13th week will be 3 weeks on transmission lines. Okay, so, all right. And I think, and 14 is going to be a review. Okay, let me share here. I have put that up on eCampus. And what I would like you to do is to remind you just where we talked a lot about different things, or at least we started it last time, but I wanted to remind you that we found, and again, please listen to me when I say that, take a piece of paper and write the most important expressions we found in the class. For example, right here, this expression, so you know that this is true, that when you have, okay, so one of the critical questions, expressions here is this one. When you have an infinite here as the problem defines, which we call the sheet of current. If it's infinite and if the current is uniform, then one of the things that you find in this one is that the tangential, the magnetic field that is excited by this infinite plane of current filaments that all go in they're infinite long, they're all parallel, and into one direction, the magnetic field that is excited is equal to the current density. That is important to remember. I don't ever want you to rederive it, but it's important to remember. The same way you should have next to you the expressions for the parallel plate capacitor, which some of you did not, I'm sure, have available next to you, so you got mixed up a little bit. Okay, and then that gave us an opportunity, because the next question is, okay, if you then tell me that the magnetic field that is excited by a plane of an infinite plane of current filaments, then what do you mean by density? So then we talked about two types of densities. One type of density is the density of current that flows only on the surface. A current flows only on the surface of a perfect conductor. You need to have a perfect conductor. And if you do, then if there is any current that flows in this conductor, it's going to only flow on its surface. The current that flows on the surface is measured, is called the surface current density. It flows on the surface and is measured, however, as amps per meter. And when you multiply those, you don't multiply them by you don't multiply the density, even if you call it surface, you don't multiply the density by a surface area, you multiply the density by a line, by length, because these currents already are infinite long along the other direction. So that's why, and you can see it here. So if I have, for example, if somebody gives me on this square, here, this is a square. If somebody, a rectangular shape, maybe better. If somebody gives me this rectangular shape and they say this is a perfect conductor and there is a current that flows in this perfect conductor, and the density, they will not even tell you what it is. They will call it the current density is, and they give you 5 milliamps per meter, for example. Then to find the total current, you will have to take that density and multiply it with the perimeter of this rectangular shape, which I have here. If you have a circular conductor like this, and there is perfect conductor, then the current flows on the surface. And then if they give you the density of the current, which is also surface current density because it flows on a surface, it's going to be in amps per meter. And in this case, to find the total current, you will have to multiply the density times the perimeter of the circle, 2 pi a. Now, we go to this case where this material is conducting, but not perfectly conducting. So what happens with conducting materials like resistive ohmic conductors, as we call them? In that case, the current flows throughout. And if the current flows throughout, we take a rod here, a rod. It looks like a cable, for example. It can be a cable out of an ohmic conductor. And then there is current, and then we assume that the current flows throughout this conductor. Then the density they will give you in this current, and usually the densities in currents, we call them S, J sub S, will be in amps per meter square, because it flows not on around a surface, not on a line, like not on the surface of the conductor, but throughout the conductor. So in this case, to find the total current, you have to take the current density and multiply it with the area of this circular conductor, of this cable. So then it's the current density times pi a square. All right, so these are the two current densities you only have. One which is amps per meter, and the other which is amps per meter square. Okay. Now from here, then we mentioned that. Did I mention this? Yes, of course I did last time. We mentioned the two properties. We said that if you have a magnetic conductor interface, and you have a current that flows on the conductor. In this case, the magnetic field that is excited by this current is related to the density of this current, which is on the surface, obviously, because this is a good conductor. And the density of this current is J sub S. But here, the relationship is a relationship that shows that is, if your current flows along the X direction, the direction of the magnetic field that is equal to that is not the X, but the Y. If the plane is XY, if this plane here, for example, or let's assume it's not a plane exactly, here is like a curved surface, but let's assume that you go here, and let's assume that in this area, where you look at the current, you have XY for the plane of the interface, and you have Z perpendicular to that. So the relationship that gives you H in terms of J sub S is this one. This relationship is not different than this one that I told you to remember. They're not different. Here, we don't see that because you have already chosen a direction, negative Z for your current. And the direction for the magnetic field is the X. So this is a special way to write, a simple way of writing the relationship that is more general, which I showed you before, and I will go back to that now. But we already wrote this relationship for this given coordinate system. So now, in the most general case, for any coordinate system, this is the way we write this relationship. So if you have a current that creates a magnetic field H, the relationship that on the surface of the conductor where the current is flowing, that relates your magnetic field that is generated by this current to the current itself is this one. Okay. Now we are trying to be more general, and instead of having a conductor magnetic, and we call the magnetic material because it has a mu r, so the relationship now becomes more general, where instead of a conductor in the green area, we have another magnetic material. So we have two materials, one that has mu1, the other that has mu2, because they have mu's which are different to mu sub naught, then these materials are called magnetic. So here it shows this relationship is the most general. And what I also want to draw your attention is to make sure that when you create this, when you write this relationship here, you always keep the order of 1 and 2 to be appropriately related with the order of, with the position, with the direction of n. When n goes from material 2 to material 1, from 2 to 1, then when your n goes like that, then the first one is h1, the second is h2. If you do not consider this order, if you don't do it correctly, then you change the direction of the current. So it's going to be wrong. So this one, it just shows that, again, this is not a good graph, but it shows that as the magnet, what does this relationship tell you? This relationship tells you that if I have a current that generates a magnetic field at the position where the current flows on the surface of an interface, then there is a discontinuity of the magnetic field. And this discontinuity, which means that there is a different value between the field in region 1 and field in region 2, right there at the current, where the current is, then this discontinuity is equal to the value of the current. While this is true, the other relationship that is also true is that the normal component of the magnetic flux density is continuous. Okay, and this is an example of how you apply these relationships in an XY system. So when you assume an XY system right at the position of the current, that's how those relationships are expressed. If there is a magnetic field that has been created by a source which is not in the vicinity where we work, it's a source that is far away, then there is continuity in the tangential component of the magnetic field and continuity in the normal component of the magnetic field. So this is the generating source, and let's assume that the generating source is somewhere there. So if I move that a little lower, that's what you have. Therefore, if your source is not on the interface but somewhere else, and you are looking at the conditions on the interface, these are the two boundary conditions, as we call them, on the interface. So the tangential component of the magnetic field are continuous. The normal component of the magnetic flux density are continuous. All right, and these are important when we solve problems. Any questions about that? Okay, this material takes us to something very important. Let's assume here, and I will draw so you can see it a little bit easier. One moment. Here's something. All right. Let's assume that I have now a coil that goes, let me see, I need to draw here. Let's assume that I have a coil, and then the coil goes around a square conductor. So let me draw the conductor first. Let's assume that the conductor, or a rectangular conductor, is like this. All right, so it's like that. And then around it, we wind a coil. And let's assume now that the coil goes like that. But let's assume that this is very close to each other, all right? That these are, we have an infinite long, and let's assume that the coil somehow starts here and goes like that. Something like this. And let's assume that we are looking at this coil. We're going inside here in this area. All right, we are here. Let's assume that the vertical dimensions are kind of, and then we are practically, I'll tell you, let's assume that we are at the center. We define the axis of this system, of this, oops, not really, where is that? Let's assume that we define the axis of this, and the axis of this different goes like that. Okay, this is the axis that goes through the center. And let's assume that we go right here and we are looking at this slice. We take a slice of this here, and we are inside and we are looking at this slice from this side. If we look at this slice here, so this is, okay, let me use this color. This is where we are, the plane, and we are on this plane, and we are looking from this side that you see the arrow. Then what you see is this one here. You see these currents flowing. This is the plane where we are. You see the currents on the top flowing away from you. You see the currents from the bottom coming towards you, all right? And you are on this plane and you observe what is happening. You look at the magnetic field. If we apply the previous conditions, because we have a conductor, all right? So this area is a conductor here, perfect conductor, all right? So this is a perfect conductor. So perfect conductor. And then also here, perfect conductor. These are also solved in your book, and I have included the sections in the book if you go on the main page. Then what you see is this picture there. And if I apply the boundary conditions as we discussed them below, I find two interesting things. I find, first of all, that the magnetic field moves along the minus X direction. Do you see here X? Well, the magnetic field goes along the minus X direction. All right, you see this direction there. And then from here. number one. Then I see something else, of course, that we saw before, that the value of this magnetic field is relating to the current. But the current, because I have all of these the circles that are created from the loops, rather, that are created from the coil that is winding around the conductor, then what I find is that H naught is JS, but JS is nothing else but the number of loops divided by the unit length, because they are so close to each other. You see that? So it's like you have a sheet of current. And we define this new parameter, N, which is like capital N, the number of loops. So where N is the number of loops, divided by the unit length. So for example, this can be measured as a number per meters. You can say, for example here, that you have along this length L, that you have N to be 100 when L equals 1 meter. So practically lower case N will be 100. All right, per meter. 100, 1/meter. That's what it is. And then, so you measure your B. And if I have the lowercase n to be 1/meter, and then mu, how do we measure mu? Is henries per meter. Then practically B comes out to be Tesla. Now, one more thing that I've noticed. Many of you have serious problems with units. So here, I saw that from the meter. So let me tell you one thing. I will write it here if I may, now that I remembered it, and I have to, all right. So 10. Let's assume that I have a solution for a current here, that I'm looking now, or the magnetic field. Somebody's asking me to find the magnetic field, and I find 10 to minus 3 volts per meter, okay? And then somebody comes and tells me, so this is the value. Then somebody comes and tells me H is 10 to minus 4 volts per meter. And that came from the units, the 10 to minus 3 and 10 to minus 4. If you were in my position, how would you grade this? Let me ask you. Would you say that if this is student A and this is student B, and this is student C, if you were a faculty member, how would you grade? And let's assume that the true answer is okay, that's the answer. What grades would you give to students? Well, A got the correct answer, all right? What grades would you give out of 10 to students B and C? Can somebody tell me? Just tell me. Okay, anybody else? I mean, let's assume that you grade. All right, so people give me some ideas. 7 for B, 3 for C. I was much more generous in this exam, but let me tell you, if the answer in the problem, if I were an engineer and I wanted to build something, this one and this one would give me a totally wrong design. So at the end, it does not matter if I am close to the solution. Both of these will give me wrong design. So if you are to be an engineer and you make an error in the units, your answer is wrong. And a wrong answer rather is dismissed. It's different now. Here we are learning, all right? So now I am generous because you're learning. But keep it one thing in mind. Many of you have a serious problem with units. You cannot put units together. I have to tell you, I saw answers from, and even accommodated, you remember that I had epsilon naught to be 8.85 times 10, and somehow the minus 12 that I had on this software that I'm running, when I made it a PDF, disappeared. So I sent an email. Let's assume I accommodated for that. So I have to tell you, if I saw that people, I looked very carefully, if I saw people had used the 10, even if I were to be very strict, I would say, you should know that epsilon naught is not 10 to minus 12. But in any case, even with that, assuming that I accommodated for this, there were people who was going from 10 to minus 9, 10 to minus 12, 10 to minus 4, and sometimes some answers had 10 to minus 4 for one capacitance, for example, and for the next capacitance, it had 10 to minus 12. You know, please be very, very careful. When you try to solve the problems, do not forget the units. If you make a mistake in one of the units, you make 3 orders of magnitude of a mistake in your answer. This answer here and this answer here, and they are not correct. This answer here is 10 times, this one is 10 times smaller than the real one. This one is 10,000 times, is 3,000, excuse me, yeah, 1,000 times smaller, or bigger rather, 1,000 times bigger than the real one. That is the impact of units. So please, 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 do you want me, maybe send me some notes if you think I should give you I should give you only exercises for units. But don't consider that units is like a side thing that you look for it at the end. The units are as important as the numbers themselves, as the solution itself. If you have a perfect solution like here, but no units or wrong units, then what can I do with that? Making, for example, an inductor that has, or an inductor that has a capacitance. Let me see, making or a capacitor, since we talked about that. Making a capacitor, which is 1 picofarads, and a capacitor, which is 0.01 picofarads, if that is the result, is very different. So I just want to say that please make sure that you don't make those mistakes. You use the units carefully. All right. Now, if we solve, since we solved the planar problem here, the other one that we can do similarly is this problem. And these problems we have already solved, both of them, one in electrostatics, the other in magnetostatics. The only reason I have them here is to show you the similarity. What is the similarity that I would like to point to? Look, that in both cases, in both cases, both for the static case, where the coaxial line is only charged with conductors, and in the electrostatic case, and the magnetostatic case, where we have a current flowing through, the fields, the difference is in one case you have an electric field, in the other case you have a magnetic field, but both the electric and magnetic field inside the coaxial, they are vary as 1/r. 1/r. That's very important. So when you find the capacitance of this, of the left, is in the form of a natural logarithm of the big radius over the small one, over the big radius of the big, this one, over the small. And if you, in the other one, you find the inductance, it's going to be the same thing. So in a coaxial, both the capacitance and the inductance vary as the natural logarithm of B over A. If B is this one, if B is the radius of the outside, and A is the radius of the inside. All right. With this, what we are going to do next time is we are going to look at similarities between these two. We have seen already those things, but we are going to only talk about the inductance. And we are going to finish with the inductance or on Wednesday. And that's how far we are going to go in magnetostatics. Okay, any questions? I have given you also the sections in the book where they discuss the same kind of geometries. And I have be careful to assign sections and examples that we are solving in the book. Any questions in the last few minutes?
Professor, not a question, but I just wanted to let you know that I was able to find my grade on Canvas. I was just looking in the wrong place.
Okay, all right, thank you. Thank you for telling me. All right, I will see you either during office hours today or on when we will have office hours today or on Wednesday.
Dr. Katehi, real quick question.
Of course.
The top hat exercise today is on inductance, but will that be?
The top hat exercise. So don't do the top hat exercise, it was on inductance. We're gonna do it on Wednesday. You can do it if you would know how to do it, but you don't, I will ask you to do it on Wednesday.
Okay, thank you.
You're welcome.
Thank you. Have a good day.
Thank you. Bye-bye.
Professor, do you have office hours today?
Yes, from 4:30 to 6:30.
Yeah, I was gonna ask you a question on Sunday, but yeah, the office hours were canceled.
Yes. Do you wanna speak with me privately, or you wanna be part of the office hours? Because if you wanna speak privately, you can come towards the end.
No, it's fine.
Okay.
It's just a general question about the
Okay.
exam, actually. Yeah.
Oh, okay. Okay.
All
All right.
Thank you.
You're welcome.
Professor,
Yes.
I was looking at the homework or like the midterm homework
Yes.
critique.
Yes.
Were there two separate problems or what? I don't know. I'm looking at it and there shows like a coaxial cable looking problem and then a parallel plate problem.
In the solution.
Yeah.
No, the other one is for the other section.
Oh, I see. Okay. Okay.
Don't do that. No, only critique. I put the solutions there just in case you want to see the other example too.
Okay. All right. Thank you.
But only for your own. Yeah.
Yeah. Yeah. I see.